Hey guys, today we'll be going over and talking about the binomial theorem. Regardless as to if you already know a lot about binomial theorem and binomial expansion, or if you just need a refresher, having a solid understanding as to what binomial theorem is, it's very important for the IB math analysis, standard and higher level courses, or just in general. It's great to know about. So yeah, it's really important to have all this stuff down. One of the things that can trip up most people and definitely messed me up when I was first learning about binomial theorem is how we can visualize or conceptualize the binomial theorem. So let's take some time to understand why binomial theorem and binomial expansion are important. First let's think about the word binomial itself. A binomial is any polynomial that has two terms, right? That has two terms. And the binomial theorem basically asks us what happens when we multiply a binomial by itself many times. So let's use as an example a plus b to the 0th, okay? So we know that a plus b to the 0th is going to be 1, right? Anything to the power of 0 is 1. That's easy. And we can see how this works through a plus b. A plus b to the first is just going to be a plus b. A plus b squared is going to be the same as a plus b times a plus b, which is going to be the same as a squared plus 2ba plus b squared. A plus b to the third is a plus b times a plus b, which is a plus b plus b plus b. And we can do a plus b to the fourth, a plus b to the fifth, and so on and so forth, right? And we can just do that. That's easy. We do FOIL, whatever. We get it, right? And we can continue this infinitely many times, but the important thing to note is that there's some kind of a pattern beginning to form. And if it's not like immediately apparent to you, that's totally fine. We'll get to the analysis portion of this soon enough. But yeah, all of this stuff can be shown in this honestly beautiful and very scary formula, which we'll also learn to understand over the course of this video. Yeah, so this is the binomial theorem. And before we get to defining these terms, let's go back to the pattern we noticed before, right? So remember how we said that a plus b to the 0th was equal to 1? Well, the rows of Pascal's triangle are conventionally enumerated starting with row n equals 0 at the top, the 0th row, which we'll get to soon enough. In this case, n is the value of the exponent to which we're raising our binomial. So when n equals 0, as is the case at the top of the pyramid, which I'll show you guys soon enough, we know that we're really just obtaining the value of a plus b to the 0th. And this also applies to the fourth row where n is equal to 3. And again, I'll show you guys some examples to help be able to conceptualize all of this, right? So here is where it all gets very interesting, right? We know that in this case, our n value is going to be this, right? So n is equal to 3 in this example. And what that is basically telling us is that we're taking a plus b to the power of 3, and n is representative of that. So here's where the variable k comes into play. And you might remember this variable coming up in the binomial theorem formula. So let's explore a plus b cubed again, right? So we know that in this case, our n value is going to be 3, since that's the power we're raising a plus b to. And let's just draw out what a plus b is equal to. We know that a plus b to the third, we got something like a cubed plus 3a squared b plus 3ab squared plus b cubed. Now let's take a look at what's happening to our n value, right? Or I guess the power that a is raised to, right? So we see that a goes from a to the third to a to the second a to the first, and then a to the 0th, right? So it's decreasing. And inversely, we see, or on the other hand, I guess, we see b starts at b to the 0th, b goes b to the first, b to the second, and then b to the third, which is very interesting. So we see the value of a goes, the power we're raising a to goes from 3 to 2 to 1 to 0, and b goes from the power that we're raising b to goes from 0 to 1 to 2 to 3. All right, so let's explore the variable k. We know that in this case, using this example again. So if we were to set up a table to express this relationship for n equals 3, we would attain something like this thing that I have down here. Yeah, so where we have k equals 0, then we have this kind of general sort of equation or formula, right? A to the n minus k times b to the k. And let's try to solve for this, right? So when we have a to the power of n, in this case, is 3 minus 0, b to the 0, right? We know that's really just the same as a cubed b to the 0th, right? Cool. And then the second one, we have a to the power of 3 minus 1, b to the power of 1, which is the same thing as a squared b1. Cool. So far, so good. And then we have a to the n minus k. In this case, again, our n is 3, so we have 3 minus 2, right? 3 minus 2, and then b squared. All of this will just give us a to the 1 and, b squared. And then we go on to the next one and so on, right? So we have a third minus 3, minus 3, and then b to the third. And all of that gives us a to the 0th, b to the third. And this can all be expressed as, let's say, a to the third. If we were to, expand this out, it could be a to the third plus a squared b to the 1, or just b, plus a to the 1, b squared, plus a to the 0th, which is 1, right? B cubed. Which, actually, if you see here, this is very similar to the values that we have up here, but we're missing those coefficients, right? Okay. So here's where we're going to get into that whole part of this. Boom, this works, but coefficients, the part of this that constitutes Pascal's triangle, are still missing, though, and here's where they come into play, right? So from where we last left off, we had a cubed plus a squared b plus ab squared plus b cubed, which is all fun and good, but isn't what a plus b cubed really equals, or what we found at the start. Well, from the very beginning of this video, we know a couple different answers for values, for different values of n. So again, an example here, we had 1, let me switch that color. 1, a plus b, and then here, of course, we had a squared plus 2ab squared, right? These colors. 2ab squared plus b, 2ab plus b squared. There. Okay, cool, sweet, nice, it's fun. And yeah, So when we look at this, we can see that the coefficients of the variables here are what forms Pascal's triangle, right? So let's try to see that. We have 1, a 1, a 1, a 1, a 2, a 1, a 1, a 3, a 3, a 1. So we have 1, 1, right? Let's just look at this, right? What this is basically saying is that we go 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And if I'm just saying 1 a bunch, I apologize. But yeah, this is kind of what it looks like, right? These are all the coefficients. And these coefficients constitute or make up Pascal's triangle. And we can use notation like n choose k, which I'll show you what that looks like this. We can use notation like n choose k to represent these variables. And the formula for n choose k equals n factorial up here, right? Sorry, n factorial over k factorial times n minus k factorial. So if you want to find what a given number is for in one of these places, you can just plug in these values, right? So you can plug in n and plug in k, and you'll be able to find them on this Pascal's triangle. And this is how we kind of represent it. And just keep in mind that the top row is row 0 and the leftmost column is 0, right? So 0, 0, 0, and 0 up here, right? So for row 0, if you were trying to find the 0th term, again, you could just plug that on. And all of this can be represented in sigma notation, right? As we know, sigma notation, sorry. Oh my God, sorry. All this can be represented in sigma notation. And as we know, sigma notation denotes the sum of many numbers. In this case, we can represent the former stuff, all that stuff from before, as this, right? So let's try to visualize that, because I don't think it'll make a lot of sense if you guys don't see it in action. But yeah, so all right. So let's go into this, right? So we have a plus b cubed. A plus b cubed equals sigma, right? K, our first value here. Well, no, k equals 0, n is 3. 3 choose k, a cubed minus k, b times k, right? So let's see what this kind of looks like. Right, okay, so this will lead us into this, something that looks... Right, so this will lead us all into something that looks like this, right? And as we go simplifying all of this, and as we go, we keep solving and whatnot, we'll be able to get like this equals 1. Sorry, let me just pull this rectangle down a little more. Yeah, okay, 1 times a to the third plus 3 times a squared b plus 3. And another quick tip, just when you're like trying to find out what these choose values are, yes, feel free to use that formula, and the formula totally helps, that n factorial over k factorial, n minus k factorial, that super helps. But honestly, it's if you can memorize Pascal's triangle and just go like 1, 1, 1, 2, 1, 1, 3, 3, 1, and then just be like, okay, cool. So this is row 0, this is row 1, this is row 2, this is row 3, and we know that n in this case is 3, so we should be looking here. Well, I know that 3, 0, the 0th term is 1, so I could just plug in like that. I know that the first term here is 3, third term is 3, so 3 choose 2, right? It gets easier. This is the second term I meant, but right. So 3 choose 2, and that's a very quick way to be able to do all of this, right? So then 3 choose 3, 0, 1, 2, 3. It's 1, so that'll be 1. 8 at the 0 with b cubed, right? And this should not be a subtraction sign. Oh my God, I'm so sorry. Ooh. Second. There we go. And that will give us a cubed plus 3a squared b plus 3ab squared plus b cubed. I really hope that was helpful, not very convoluted. And yeah, happy solving and good luck.